Okay, it's 40 after whatever hour it is in your time, so I'm going to get started and restart at that copy of the opening screen. Okay, good day, Sydney. And good day is a very appropriate greeting, as in Sydney, it's time to say good morning, but here on the east coast of the USA, it's time to say good evening, and very soon, good night. Don't we just love time zones? No, we don't. Yet another reason I'd much rather be there in person, but at least up here I'm safe from the drop bears. Anyway, good day, y'all. I'm Dave Aronson, the T-Rex of Codosaurus, and I'm here to teach you to kill mutants. But first, I think we should level set some expectations. First, this isn't exactly an advanced talk within its topic, nor is it a beginner level talk, and even averaging them out and calling it an intermediate talk would not quite do it justice. What this is an introduction to an advanced topic. Second, a bit of a confession. I do not consider myself an expert on mutation testing. One of the dirty little secrets of public speaking is that you don't have to be an expert. You just have to know a little bit more about something than the audience, enough to make the talk worth their time and be able to convey it to them. And mutation testing is still rare enough that most developers have never even heard of it. So let's start with the basics. What on infinite earths is mutation testing? In our universe, that of software development, not comic books, it's a software testing technique. Surprise! Thank you, Captain Obvious. But why is this one different from all the others? One might look at the name and think, well, obviously it's about testing the mutations used in genetic algorithms. But no, the big difference is that most other testing techniques are about checking whether or not our code is correct. Mutation testing, however, assumes that our code is correct, at least in the sense of passing its unit tests. Of course, this means it also assumes that we already have unit tests. Instead, mutation testing is about checking for two different qualities. In my opinion, the more important, helpful, and interesting of these two qualities is not something about our production code at all, but that our unit test is strict. To check this, a mutation testing tool will find the gaps in our test suite that let our code get away with unintended behavior. Once we find gaps, we can close them by either adding tests or improving existing tests. Lack of strictness comes mainly from lack of tests or poorly written tests or poorly maintained tests, like ones that didn't keep pace with changes in the code. Speaking of which, the other thing mutation testing checks is that our code is meaningful, by which I mean that any little change to the code will produce a noticeable change in its behavior. Lack of meaning comes mainly from code being unreachable, redundant with other code, or otherwise just not having any real effect. Once we find meaningless code, we can make it meaningful if that fits our intent, or just remove it. Mutation testing puts these two together by testing that every possible tiny little change to the code, within reason, does indeed change the code's behavior, and that the unit test suite does indeed notice that change and fail. Not all the tests have to fail, but each change should make at least one unit test fail. That's the positive side, but there are some drawbacks. As Fred Brooks told us back in the 1980s, there's no silver bullet. Besides, those are for killing werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually rather slow. We certainly won't want to mutation test our whole code base on every save. Maybe over a lunch break for a smallish system, or overnight for a larger one, maybe even a weekend. Fortunately, most tools let us just check specific files, classes, modules, functions, and so forth. Plus, they usually include an incremental mode, so that we can test only whatever has changed since the last mutation testing run, or the last commit, or some other such milestone. That maybe we can do on every save for a very small system, or at least over a shorter break for the rest. Its CPU-intensive nature can also really run up our bills on cloud platforms such as AWS or Azure, however you pronounce it. Another drawback is that mutation testing is not at all a beginner-friendly technique. It tells us that some particular change to the code made no difference to the test results. But what does that even mean? It takes a lot of interpretation to figure out what a mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with a much bigger vocabulary, so they're not always on about brains. They're usually trying to tell us that our code is meaningless, or our tests are lax, or both, but it can be very hard to figure out how. Even worse, sometimes it's a false alarm, because the mutation didn't make a test fail, but it didn't make any real difference in the first place. It can still take quite a lot of time and effort to figure that out. Even if a mutation does make a difference, there is normally quite a lot of code that we shouldn't bother to test. For instance, if we have a debugging log message that says the value of x is, and then the value of x, that constant part will get mutated, even though we don't really care. Fortunately, most of the tools have ways to say, don't bother mutating this line, or even this whole function, maybe this file. But that's usually with comments, which can clutter up the code and make it less readable. Now that we've seen the pros and cons, how does mutation testing work, unlike the guy in this silhouette? It mutates copies of our code, hence the name. It does this to create test failures, also known as faults. So mutation testing can be categorized as a fault-based testing technique. This means it is related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix discover flaws in their error recovery, mutation testing helps us discover flaws in our tests and our code. But the way mutation testing does this is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults, such as dropped connections, into Netflix's production network. If all goes well, in the sense that Netflix's customers don't notice and their metrics are still good, then Netflix knows that their error line. Mutation testing, however, injects semantic changes, not necessarily problems. It doesn't usually know whether these semantic changes will create faults or not. We certainly hope they all will, but that depends on the test suite. It injects them into copies of our code, not our actual network. And it does its work in our test environment, not production. And if everything still goes well, in the sense that our unit tests all still pass, that does not mean that all is well. That means that there is a problem. Remember, each change to our code should make at least one unit test fail. Mutation testing has also been compared to fuzzing or fuzz testing, a security penetration technique involving throwing random data at an application. Mutation testing is somewhat like fuzzing our code rather than fuzzing the data, but it's generally not random. Most mutation testing engines apply all the mutations that they know how to do, the smarter ones, can use the results from some simpler mutations so that they know they don't need to bother with some more complex mutations. But even then, it's not random. But enough about differences. What exactly does mutation testing do and how? Let's start with a high-level view. First, our chosen tool breaks our code apart into pieces to test. Usually these are our functions, or methods if we're using an object-oriented language, but I'm just going to say functions. Then for each function, it tries to find the function's tests. If the tool can't find any tests, most will simply skip this function. Better yet, most of those will warn us, so we know we should go add or annotate some tests. More on that later. Some, though, will use the whole unit test suite, which is horribly inefficient and leads to even more false alarms. Anyway, assuming we aren't skipping this function, next the tool makes the mutants. To do that, it looks closely at the function to see how it can be changed. For each tiny little way this function can be changed, the tool makes one mutant with that one tiny little change. Once our tool is done creating all the mutants it can for a given function, it iterates over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. The tools generally don't give us any such sort of thing, but it's a conceptual model I'm using to help illustrate the point. For each mutant derived from a given function, the tool runs the function's unit tests, but it runs them using the current mutant in place of the original function. If any test fails, this is called, in the standard industry terminology, by the unfortunate name of killing the mutant. However, some people object to this violent communication, especially since in the comic books, mutants are often metaphors for marginalized groups, and the tech industry is starting to become more sensitive to such issues. So let's take a brief detour into some nicer terminology I'm trying to come up with. So far, I'm leaning towards terms like rescuing, or better yet, covering the mutant. This makes sense if you think about it in terms of what really happens in mutation testing and in normal testing. In normal use of test coverage, normal code should be covered by at least one test and let all tests pass. By way of analogy, in mutation testing, mutants should be covered by at least one failing test. Remember, each change should make at least one unit test fail. Unfortunately, the term covered is already used to mean that the mutated code is run by at least one test, whether failing or not, much like the normal concept of test coverage. So I'd like to replace that with saying that the mutant is exercised or maybe run. But it's a long, hard uphill battle trying to change terminology that people are already using. Oh well. Anyway, whatever we call it, when a mutant makes a unit test fail, and I'm going to stick to the standard terminology of killing it in this presentation, each mutant should make at least one unit test fail. So when it does, that's a good thing. It means that our code is meaningful enough that the tiny change the tool made to create this mutant actually made a noticeable difference in the function's behavior. It also means that our test suite is strict enough that at least one test actually noticed that difference and failed. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it could make fail, like perhaps some of tests 6 through 10 for mutant number 1 on this chart. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the unit tests pass, then the mutant is said to have survived. That means that the mutant has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both. And now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some of the technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree. There are some tools that work differently, like working on bytecode, and some even work on the actual text of the source code. But most use an AST, so let's roll with that. And I know those boxes are too small to read well, but we don't need to understand this one in detail. After our mutation testing tool creates an AST out of our code, then it traverses the tree looking for subtrees, or branches, if you will, that represent our functions. After finding them, it handles them as I described it before, starting with looking for each one's tests. But how does it do that? That usually relies mainly on us developers, either annotating our tests, as I mentioned earlier, or following some kind of naming convention. This is often supplemented and sometimes even replaced by having the tool look at what unit tests call what functions. However, that can get tricky if the function isn't called directly from the test. In that case, it usually involves looking at test coverage data or some other such gathered information. After the tool has found the function's tests, then, assuming it won't skip this function because it didn't find any tests or whatever other reason, it makes the mutants. To make mutants from an AST subtree, it traverses that subtree just like it did to the whole thing. However, now, instead of looking for even smaller subtrees it can extract, like twigs or something, it looks for nodes where it can change something. Each time it finds one, then for each way it can change that node, it makes one copy of the function's AST subtree with that one node changed in that one way. For instance, suppose our tool has started traversing the AST I showed earlier and has only gotten down to this while loop following that arrow. For each way it could change that node, it would make a fresh copy of this whole subtree with only that node changed in that one way. After it's done making as many mutants as it can from that node, it would continue traversing the subtree down to that node's first child node, the conditional that controls it, a not equal comparison. Again, for each way it could change that node, it would make a copy of this whole subtree with only that mutation, and so on until it has traversed the entire subtree. Now, I've been talking a lot about mutating things and changing them. So what kind of changes are we talking about? There are quite a lot. You could change a mathematical, logical, or bitwise operator from one to another. In languages and situations where we can do so, it could even substitute an operator from a different category. For instance, in many languages, we can treat anything as Booleans. So x times y could become, for instance, x and y, or x exclusive or y. Order of operands matters, such as in subtraction, division, or exponentiation. It could swap them. It could change a comparison from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It could remove entire lines of code, though usually because it's a statement rather than looking at the physical written lines of the source code. It can remove a condition so that something that might be skipped or done is always done. It can remove a loop control so that something that might be skipped, done once, or done multiple times is always done exactly once. It could scramble or truncate argument lists of function calls. Truncation will often result in a syntax error from having the wrong number of arguments. However, if our language allows default or variadic arguments, this could be perfectly fine. It could also scramble or truncate argument lists of function declarations. This will usually result in a syntax error where it's called from because of the call having too many arguments, or inside the function from having an unknown variable, but sometimes not. When the call still works, that can help reveal times when we've got a parameter shadowing a variable in an outer scope, in other words, using the same name. That isn't necessarily wrong, but it can be dangerous, or at least confusing, making for bad maintainability. It could replace a function's entire contents with a constant or any of the arguments, or raising an error, or nothing at all if the language permits, as many do. It could change a constant or variable or expression or function call to some other value. It could even change it to something of an entirely different and incompatible type, such as changing a number into a, if I may quote Smeagol, string or nothing. There are many, many more, but I trust you get the idea. From here on, there are no more low-level details I want to add, so let's finally walk through some examples. We'll start with an easy one. Suppose we have a function like so. Think about what a mutant made from this might return, since that's what our unit test would probably be looking at. Mainly, such a mutant could return results such as any of these expressions or constants, and many more, but I had to stop somewhere. Now suppose we had only one test, like this. This is a rather poor test, but even so, most of those mutants on the previous slide would get killed by this test, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason a tool would put a 4 there, as opposed to 0, 1, or other significant numbers. Subtracting gets us 0, dividing gets us 1, returning either argument gets us 2, and the error conditions will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order all get us the correct answer. Therefore, these mutations, or rather any mutant based on these mutations, would survive our test. We know this because when we run our tool, it gives us a report that looks roughly like this. The exact words, format, amount of context, and so forth will depend on exactly which tool we use, but the information should be pretty much the same. And that is that if we changed the function called power, which is in file demo.rb and starts at line 42, in any of 4 different ways, then all its unit tests would still pass. And those 4 ways are to change line 42 to swap the arguments, or change line 43 to change the exponentiation to addition or multiplication, or to change line 43 to swap the operands. So what is this set of surviving mutants trying to tell us? The very high-level message is, of course, that our test suite is not sufficient, either because there aren't enough tests or the ones we have just aren't very good, or both. But so we should ask ourselves, how are these mutants surviving? Are they pulling heists? Are they living at the Xavier Institute? Or what? The usual answer is that they give the same the same result as the original function. Or if we're not doing pure functional programming, maybe they have the same side effect. Whatever it is that our tests are looking at. To determine how that happens, we can take a closer look at one mutant and a test it passes. Let's start with the plus mutant. Looking at the change together with our test makes it much clearer that this one survives because 2 plus 2 equals 2 to the second power. So how can we kill this mutant? In other words, make it return a different answer than the original code given some set of inputs. It's quite simple in this case. We just need to make at least one test use arguments such that x to the y is different from x plus y. For instance, we could add a test or change our existing test to something like this, to assert that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. 2 plus 4 is 6, not 16, so this should kill the plus mutant just fine. For that matter, 2 times 4 is 8, which is also not 16, so this should kill the times mutant as well. However, the argument swapping mutants still survive. How can that be? It's because 2 to the 4th power and 4 to the 2nd are both 16. Seeing as this function deals with powers, it might have been smarter to use arguments where either one is a power of the other. But anyway, we can attack those argument swapping mutants separately. No need to kill them all in one fell swoop and be some kind of superhero about it. To do that, again, we can either add a test or adjust an existing test to something like this, to assert that 2 to the 3rd power is 8. 3 squared is 9, not 8, so this kills the argument swapping mutants. 2 plus 3 is 5, 2 times 3 is 6, and both of those are not 8. So the plus and times mutants stay dead, and we don't get any zombie mutants wandering around. With these inputs, the correct operation is the only simple common one that yields the correct answer. This isn't the only solution, though. We could have used 2 to the 5th, 3 squared, 3 to the 5th, vice versa, and many, many more. There are lots of ways to skin that flurkin. This may make mutation testing sound simple, but this was a downright trivial example, so we could easily think up arguments to make all mutants, within reason, behave differently from the original code. So let's look at a more complex example. Suppose we have a function to send a message, like so. This function, sendMessage, uses a loop that sends as much data as sendBytes can handle in one chunk, over and over, picking up where it left off, until the message is all sent. This is a very common pattern in communication software. A mutation testing tool could make lots and lots of mutants from this, but one of them of particular interest would be this, removing those lines with the minus signs, an example of removing a loop control. That would make it effectively read like this. Now, suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a bit more that I'm not going to show you quite yet, dealing with setting the size and creating the message. But even without seeing that code, what does the survival of that non-looping mutant tell us? If a mutant that only goes through that while loop once acts the same as our normal code, as far as our tests can tell, that means that our tests are only making our code go through that while loop once. So what does that mean? By the way, you'll find that interpreting mutants involves a lot of asking, so what does that mean? And recursively. But in this case, it means that we're not testing sending a message larger than sendBytes can handle in one chunk. The most likely cause of that is that we simply didn't test with a big enough message. For instance, suppose our maximum chunk size, what sendBytes can handle in one chunk, is 10,000 bytes. However, for whatever reason, we're only testing with a tiny little 3-byte message. Or maybe 4 if we include a null terminator, whatever. The obvious fix is to use a message larger than our maximum chunk size. We can easily construct one as shown here. We just take the size, add 1, and construct that big a message. But perhaps, to paraphrase Shakespeare, the fault, dear Sydney, is not in our tests but in our code that these mutants are survivors. Perhaps we did test with the largest permissible message. out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes. We tested with a large, and yet this mutant survives. In other words, we're still sending the whole message in one chunk. What could possibly be wrong with that? What is this mutant trying to tell us now? It's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the loop control, we wind up with this code I showed you earlier. And if we rerun our mutation testing tool on that, it will show a lot of other stuff as now being redundant, because we only needed it to support the looping. If we also remove all of that, then eventually send message boils down to this. And now it's pretty clear. The entire send message function may well be redundant, so we can just use send bytes directly. Now, mind you, it might not be, because in real-world code, there may be some logging, error handling, and so forth needed in send message, but at least the looping was redundant. Fortunately, when it's this kind of problem with unreachable or redundant code, the solution is clear and easy. Just chop out the extra junk that the mutant doesn't have. This will also make our code more maintainable by getting rid of useless cruft. Now that we've seen a few different examples of spotting bad tests and redundant code, some of you might do better staring at code than hearing me talk about it. So here's some pseudocode showing how mutation testing works from a very high-level view. I'll pause a moment for you to read it or take screenshots. All right, moving on. I assume you know how to take a screenshot pretty fast. I'd like to address some occasionally asked questions. Mutation testing is still rare enough that I don't think there are any frequently asked questions. First, this all sounds pretty crazy, deliberately making tests fail to prove that the code succeeds. Where did this whole bizarro idea come from anyway? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool didn't appear until 9 years later, in 1980, as part of Timothy Budd's PhD work at Yale. Even so, it was still not practical for most people until recently, maybe the past couple decades or so, with advances in CPU speed, multi-core CPUs, larger and cheaper memory, and so on. That leads us to the next question. Why is it so CPU intensive? To answer that, we have to do some math, but don't worry, it's very basic. Suppose our functions have, on average, about 10 lines each. And each line has about 5 places where it can be changed to any of about 20 alternatives. That works out to 1,000 mutants per function. And for each one, we'll have to run somewhere between 1 unit test if we're lucky and kill it on the first try, and all of that function's unit tests if we kill it on the last try, or worse yet, it survives. Suppose we wind up running just 1/10 of the tests for each mutant. Since we start with 1,000 mutants, that's still 100 times the test runs for that function compared to just running the tests. If our unit test suite normally takes a zippy 10 seconds, mutation testing will take about 1,000 seconds, which might not sound like much because I'm saying seconds, but do the math, and it's almost 17 minutes. But there is some good news. Over the past decade or so, there's been a lot of research on trimming down the number of mutants, mainly by weeding out those that are semantically equivalent to the original code, redundant with other mutants, or trivial in various ways, such as creating an obvious error condition. Such things have reduced the mutant horde by up to about 2/3. But even with that rare level of success, it's still no silver bullet, as this takes a lot of CPU time itself. and the remaining mutants are still quite a lot. The next question is, when making each mutant, why change it in only one way? There are multiple reasons. For one, it helps us poor humans focus. It's much easier to tell what a surviving mutant is trying to say if we're only talking about one thing at a time. You can think of it like using the single responsibility principle. Another reason is that multiple changes may balance each other out, leading to more false alarms. For instance, remember that first simple example and its argument swapping mutants? If one mutant had both of these mutations, then first would swap the arguments and the other would swap them right back for no net effect. So it would survive pretty much any unit test you could possibly throw at it. Lastly, allowing multiple mutations would create a combinatorial explosion of mutants, with the tool making many, many times more mutants per function, which would make it even more CPU intensive. I'll spare you the math, but with our earlier code size assumptions, even if we manage to weed the mutants down by 2/3 at each step, with one mutation per mutant, we'd have 333 mutants per function, and a third, but I'm rounding. With two, we'd already have almost 110,000. And with three, we'd still have over 35 million. Never mind actually running the tests, just creating the mutants would get to be quite a heavy workload. But we can avoid this huge workload and the increased false alarms and the lack of focus if we just limit it to one mutation per mutant. The last question is, this sounds like it only makes sure that our unit test suite as a whole is strict. Is there any way it can help us assess the quality of individual tests? Yes, there is, but it would take a lot longer. You may remember how I said early on that when a mutant makes a unit test fail, the tool will stop running any more tests against it, mark it killed, and move on to the next one. So when we're done with a given function, we wind up with a chart like this. Again, remember the tools don't actually give us a chart. It's just a conceptual model I'm using to illustrate the situation. If we were to run the rest of the tests, that would take a lot longer, but it would give us some useful information that we can use to assess the quality of some individual tests. Look at tests 4 and 9. None of the mutants make either of those fail. Now, this isn't an absolute indication that they're no good, but it does mean that they might merit a closer look, somewhat like a code smell. However, I have not seen this feature actually implemented in any mutation testing tool. If you do find one that will let you run all tests against all mutants and gives you this full of a report, I suppose you could take this concept a step further and look next at those that only stop one mutant and then two and so on. But I think it would rapidly reach a point of diminishing returns. I'd probably stop at 0. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's easy to get started with in terms of setting up most of the tools and annotating our tests if needed, which may be tedious, but at least it's easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean it's not a good fit for our particular current projects, though, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of some popular tools for some popular languages and platforms, and some others. I doubt many of you are doing Fortran 77 these days. I'll talk a bit so you have time to take screenshots. Just be aware that many of these are outdated. I don't know or follow quite all of these languages and platforms. The ones I know are outdated are crossed out. There's also a promising tool called Wodl Test, a language-independent mutation engine with which you can make language-specific mutation testing tools. Sorry, I haven't looked into it much myself. Before we get to Q&A, I'd like to give a shout out to TopTal, a consulting network I'm in whose speakers network helped me prepare and practice this presentation. Please use that referral link if you want to hire us or join us, and that's also the destination of that QR code. Also, many thanks to Marcus Sherp, who created Mutant, the main tool I've actually used for Ruby, and he's been very willing to answer my ignorant questions and critique this presentation. And now it's your turn. If you have any questions, I'll take them now. If you think of anything later, I'll be around for the rest of the conference, including some of the after party, but that'll be starting at about 1 a.m. my time. Or if you think of anything after the conference, there's my contact information up there. So, any questions? I'm not seeing anything in the chat. So, if a pass is a fail and a fail is a pass, this is starting to sound like something amusing. What do we really call the fails? Well, it depends at what level you mean fail. If you mean that, okay, says, sorry, no joke. Well, if you mean what do we call it when the mutant makes the unit test fail, that's what we call killing the mutant, and that's actually the objective. We want all the mutants to get killed by at least one test. With most tools, each one will only get killed by one test, because then it will stop running any more tests against that mutant. There's something else you meant by the fails. You were wondering what it meant, what we would call them, then please clarify in the chat. Meanwhile, I'll just guess that maybe if you mean we have failed to achieve the objective of making a unit test fail, that's that the mutant has survived. The tools give us a report of the surviving mutants that did not get killed, in other words, did not make a unit test fail. In other words, let all the unit tests pass. Those are the ones that we need to figure out, okay, what are they trying to tell us? Mainly, what sort of test are we lacking? Or where do we have code that may be redundant or unreachable or otherwise without any effect? All right, next. In your experience, when would you run these? It seems like it would blow up a gated check-in. When do you think it would be best used? I have seen this used in a gated check-in, such as a step in a CI or CD pipeline. However, the trick is how you set the requirements. Ideally, we should have 0 surviving mutants, but it's going to take a long time to get there on any already established code base. So just like some tools will analyze that the percent test coverage has at least not decreased, you could set up something to say your number of surviving mutants has not increased. Or just like you can only mutation test what has changed since the previous commit, you could have something demand that there be 0 surviving mutants in the code of this commit, or of this pull request that may have multiple commits. Let's see. Report of surviving mutants. That's the answer. Okay. As a separate work item to evaluate the tests. Not sure what you mean, Bill, but yes, you could use the results of a mutation testing report to create a ticket or whatever, some sort of work item to say, hey, go look at these mutants, figure out what they're trying to tell us, and perhaps either fix the issues or make further tickets. Perhaps they're trying to tell us, okay, we've got these 50 bazillion files that have like absolutely meaningless tests. They may have 100% coverage, but the coverage doesn't really mean much. They're bad tests. So you could make additional tickets to say, okay, slap some meaningful tests around this file and another one for that bunch of files or whatever. Okay, I'm not seeing anything further. Unfortunately, I cannot actually see the Slack room right now. Come to think of it, yes, maybe I can on my secondary device, my tablet. Is anybody putting anything in there? That's pretty straight. Oh, we somehow managed to switch rooms. Okay, let me get to the right room. It can switch operators, so it's a junior developer, but bum. Okay. Okay. In a greenfield development, do you include this from the very beginning? Sorry, first time I ever heard of this concept. Well, it's probably the first time a lot of the people at this conference have heard of it. Like I said, hardly anybody has really heard of it, despite the fact that it's been around for, well, longer than most of us. And yes, I would recommend including it from the beginning in a greenfield project because, number one, it'll help you create more meaningful tests. I've been, in fact, toying with the idea of starting a little toy project with just one test that just does like assert true and then like pick a random mutant, kill it, lather, rinse, repeat, and see if that helps me generate a good test suite with the guidance of mutation testing. I'm not advocating that yet, but it's an idea that I'm toying with. The other benefit, of course, it will help keep your new code base shiny and clean and lean and devoid of unreachable code and other meaningless cruft. Okay, follow on from your previous response. What did you mean by having 100% test coverage, but the tests being meaningless? Okay. Of course, we all try to get really high test coverage. Maybe we don't aim for 100%, but hey, nice goal. But you can get there by cheating. You can have code that, you can have tests, that runs your code, but doesn't do anything meaningful with it and then does assert true. That'll get you 100% code coverage. You could possibly even have a very small number of tests that call some of your high-level functions that call a bunch of other stuff down below so as to run huge swaths of code for each test, but not really look at it, not look at the results or side effects or whatever. So while a properly written test would be, meaningful, it would actually test something significant, I'm not going to trust that everybody's tests are really good. Does that, you understand what I mean? Not seeing any response. So I will assume that does answer the question. Okay, I'm not seeing anything more in the Slack room. Thanks, but most people wouldn't be doing assert true. Well, that depends how closely they think their tests actually get looked at, how honest they are, how skilled they are, and so forth. I think we can all think of at least a few developers who certainly would if they, number one, were being pressured to get 100% test coverage or any high number, and secondly, thought they could get away with it. Of course, you and I wouldn't do that, but I think we know some who would. Yeah. Okay. Any more questions? Or should I just give you your, do I have a link to those awesome slides? Most times I actually do put them up in advance as a way to sort of prevent myself from continuing to mess with them at the last minute, which we all know is a bad idea, but we often still do it. But I was out of town for a while, couldn't work on them, had some additional ideas I wanted to get in there. So no, I do not have them available yet, but I can export them to PDF and put them up somewhere. And I'll maybe drop a link in the hallway or this room if I can do it very quickly. Let's see. Anything else? Or you want 9 minutes of your night back? I'm not seeing further questions, so I guess I'll give you 9 minutes of your night back. So, night, everybody.
Thanks.